First of all, let me thank the organizers for this wonderful opportunity to give a talk in this form. It's a really nice idea to organize a workshop in these pandemic days. In this talk, I'm going to present some recent results on acyclic, star, and injective colorings, and all results are obtained in joint work with Petr Golovach, Barnaby Daniel Paulusma, and Siani Smith. Many graph theoretical problems are known to be NP-hard, and it's a natural way of increasing our understanding of these problems if we restrict the input. In our case, we are interested in bounding the diameter, and we ask the following question: how much does bounding the diameter help for obtaining some polynomial time algorithms for well-known vertex partition problems? So let's start with three well-known vertex partition problems, and these are k-coloring, click, and independent set. Well, it's easily seen that all graphs of diameter 1 are complete, and as our problems are easily solved on complete graphs, it's not a big surprise that these problems become polynomial time solvable if we restrict the input to graphs of diameter 1. However, as soon as we allow graphs to have a diameter 2, we find that most of our problems remain NP-complete. And the reason is we can reduce from 3 coloring, click, and independent set by the following graph transformation. Take a graph G, add a complete graph on k-3 vertices, and make each vertex of the complete graph adjacent to each vertex of G, and you find that the obtained graph has a diameter 2. Well, you see that this trick only works if the complete graph is non-empty. In other words, k has to be at least 4. And so we see that this trick only shows that 4 coloring is NP-complete on graphs of diameter at most 2. In other words, there might be some hope if we consider 3 coloring. However, it's easily seen that 3 coloring is NP-complete on graphs of diameter at most 4, and there's a highly non-trivial proof that also shows that 3 coloring is NP-complete on graphs of diameter at most 3. And so we find that for click and independent set, our observation gives a complete solution, but for the k-coloring problem, there's one open case. And this open case is where we consider the 3 coloring problem for graphs of diameter at most 2. As there's an open case for the k-coloring problem, we ask ourselves what happens if we consider variants of coloring problems. Are there some variants for which this open case is polynomial time solvable? And indeed, there are some variants. For example, acyclic k-coloring. In general, vertex coloring of a graph G is acyclic if taking any 2 color classes of the vertex coloring, we find that the union of these 2 color classes induces a forest. In other words, an acyclic vertex coloring is so that we forbid bichromatic cycles. By this definition, we clearly can define the acyclic k-coloring that asks, given a graph G, if that graph has an acyclic k-coloring. You may ask, why do we fix the integer k? Well, that's easily answered. Somehow similar to the 4 coloring problem, we can show that the acyclic 4 coloring problem is NP-complete on graphs of diameter at most 2, and so clearly the general problem where k is part of the input and not fixed is NP-complete on graphs of diameter at most 2. And as we already mentioned, if we consider graphs of diameter 1, we find that these are complete graphs, and of course the acyclic coloring problem on complete graphs is also solvable in polynomial time. So let's go to the acyclic k-coloring problem. Well, first of all, let me mention that if k is at least 4, then we obtain some similar results as for acyclic k-coloring. The only difference is that we reduce in the NP-complete case from acyclic 3 coloring, which also is NP-complete. So let's focus on the first line. That means we study acyclic 3 coloring. Here we can prove that our open case, namely that where we consider graphs of diameter at most 2, becomes polynomial time solvable. However, if we allow graphs to have a diameter at most 5, then our problem remains NP-complete. So how can we find that acyclic 3 coloring is polynomial time solvable on graphs of diameter at most 2? Well, we have a little lemma that gives us some structural characterization of the acyclic 3 colorable graphs of diameter at most 2. If we have such a graph, then we find an acyclic 3 coloring, let's call it C, such that we have to remove at most one vertex, and in the obtained graph we find an induced 2p2 whose neighborhood is one of the color classes of C. Furthermore, we find that if we remove this color class from G, then we find that the remaining graph has at most 2 components, and as our graph is acyclic 3 colorable, in particular C is an acyclic 3 coloring, we find that each of these 2 components must be a tree. How can we make use of this lemma? Well, given a graph of diameter at most 2, we consider all possible selections of our set S and an induced 2p2. Please note that as in the set S there is at most one vertex, we find at most polynomially many selections. For each of them, we compute the neighborhood of the induced 2p2. If such a neighborhood is an independent set, then remove it from the graph G and check if the remaining graph is an induced forest on at most 2 components. If the remaining graph is such an induced forest, we know that there are up to symmetry at most 2 colorings. Each of these 2 colorings can be extended to a 3 coloring by adding the vertices of the independent set as a third color class. So for all selections of our set S and the induced 2p2, we find at most 3 colorings of the graph G, and for each of these 3 colorings we check if it is indeed an acyclic 3 coloring, and so we can solve acyclic 3 coloring on graphs of diameter at most 2. Okay, so let's restate our main theorem for acyclic K coloring again. As you see, there are 2 open cases for acyclic 3 coloring, but I have to say very recently Pascal joined the project and we were able to reduce the 5 in the NP-complete case to a 4, and so the only open case that is left is that where we consider acyclic 3 coloring on graphs of diameter at most 3. At this point, let me mention that the open case for the K coloring problem becomes polynomial time solvable for the acyclic K coloring problem, but at the same time we obtain a new open case, and so it's quite a natural question to ask if there are variants of acyclic K coloring for which this problem becomes polynomial time solvable. We will show in a minute that star K coloring is such a variant. A vertex coloring in general is a star coloring if the union of every 2 color classes induces a graph which has no 4 path. In other words, the union of every 2 color classes induces a C4 and P4 free graph. As I already mentioned, a star coloring is a special acyclic coloring, and such a star coloring can be also defined as a vertex coloring which forbids bichromatic P4s. Somewhat similarly to the acyclic K coloring problem, we can define the star K coloring problem, and again similarly we can show that a problem where K is part of the input is NP-complete whenever we consider graphs of diameter at most 2, and polynomial time solvable if the input is restricted to graphs of diameter 1. For that reason, let us focus on star K coloring, and it's not a big surprise that we obtain some similar results if K is at least 4, since the star 3 coloring problem is NP-complete as well. That means we can focus on star 3 coloring, and here we find that indeed our open case for the acyclic K coloring problem becomes now polynomial time solvable if we consider star 3 coloring, and we also obtain that the star 3 coloring problem remains NP-complete if we restrict the input to graphs of diameter at most 8. At this point, let me sketch our polynomial algorithm. Well, first of all, we do some pre-calculations. For example, we test for 5 cycles. Suppose for a contradiction that a star 3-colorable graph has a 5 cycle. We pick such a 5 cycle and we easily see that there are 2 vertices which are non-adjacent but which receive the same colors, and they have a common neighbor which of course receives a different color. We now see that one of the 2 four-paths is bichromatic, or the remaining 2 vertices receive the 3rd color. However, the remaining 2 vertices are adjacent, and so in all cases we obtain a contradiction. That means if we have a star 3-colorable graph, this graph has no 5 cycle. So for that reason we test for 5 cycles and assume that G has no 5 cycle. Next we test for false twins. Assume in a star 3-colorable graph there is a 4th cycle. Somehow similarly to the case where we considered 5 cycles, we find again 2 non-adjacent vertices which receive the same color and which have a neighbor which of course has to receive a different color. As there are no bichromatic four-paths, we find that the last vertex in this cycle has to receive the 3rd color. We now prove that the 2 vertices which receive the same color have degree 2 in our graph. So suppose for a contradiction that one of these vertices has a neighbor outside. Of course, we cannot color this vertex by color 2 as it's adjacent to a vertex of color 2, and so we have to use color 1 or color 3. But now we find a bichromatic four-path, just depending on which color we assign to this vertex. In other words, if we have a 4 cycle, then we find at least 2 vertices which are of degree 2. And so if we have a set of false twins, then we know that all of these false twins are of degree 2 and all of these vertices have to receive the same color in a star 3 coloring. So that means we can simply remove all but at most 2 vertices from any set of false twins. We next compute the maximum degree of our graph. If the maximum degree is somehow small, then of course we know as the diameter is bounded, the order of our graph is bounded, and we can solve the star 3 coloring problem in constant time, and so we can assume that the maximum degree of our graph is sufficiently large, and in our case it suffices to assume that the maximum degree of our graph is at least 5. Okay, before I introduce our last preliminary result, let me sketch the main idea of our algorithm. In general, it can be described as follows. Given a graph G, we pre-color some vertices of G and try to extend this pre-coloring to a star 3 coloring of the complete graph. For the extension itself, we have some well-known tools. In our case, we apply the two-list coloring problem, which is known to be solvable in linear time. However, this approach has a little problem. If you have a pre-coloring and apply the two-list coloring problem to extend this pre-coloring, you obtain a coloring, but this coloring is not necessarily a star 3 coloring. For that reason, we introduce our last preliminary result, and that's a supergraph of G, which can be constructed as follows. For each edge, say E of our graph G, we add a new vertex and make this vertex adjacent to the 2 end vertices of our edge E. For all other edges that are vertex disjoint from E, but which are of distance 1, we add an edge between the 2 new vertices. And that way we obtain our supergraph. And as it's easily seen, our graph G is star 3 colorable if and only if our supergraph is 3 colorable. With the supergraph, we are now in a position to apply the two-list coloring approach, and we are in a position to describe our main algorithm. In general, we construct linearly many two-list assignments of our supergraph, which are polynomially equivalent to the star 3 coloring problem on G. How do we construct these two-list assignments of our supergraph? Well, first of all, we fix a vertex of maximum degree in the graph G. As G is of maximum degree at least 5, we know that this vertex, say it's V0, has at least 5 neighbors. Furthermore, we assume that we assign color 1 to V0. We proceed by assigning lists of size at most 2 to the vertices of G. Well, in the first case we assume that there's a star 3 coloring which assigns all the neighbors of the vertex V0 the same color. Let's say color 3. As in a star 3 coloring there are no bichromatic 4 paths, we find that all vertices of distance 2 to V0 have to be colored by color 2. And so all the vertices which are of distance 3 have to receive color 1 or color 3. And so you see we now have a list 2 assignment of G, and that can be easily extended to a list 2 assignment of the supergraph of G. Okay, so let's proceed with case 2, and here we assume that not all neighbors of V0 receive the same color. As V0 is of degree at least 5, we find that at least 3 neighbors of V0 are colored alike, and that there is at least one vertex which receives a different color. So we consider all possibilities of selecting a set W which consists of 3 vertices, and all these vertices are colored by color 3, and we consider all possibilities of selecting a set X which is of size at least 1, and we color the vertices in X by color 2. Of course, there might be some further vertices, and these have to be colored by color 2 or 3. But if there's an edge, for example, between a vertex in X and a vertex in Y, then we easily see that we can remove color 2 from the vertex in Y and shift this vertex to W. In other words, we can update the sets W and X in such a way that if there's an edge between 2 neighbors of V0, then one end vertex is in W and one end vertex is in X. Okay, so let's go to the vertices which have distance 2 to V0. Well, first of all, let W star be the set of vertices which have a neighbor in W. As in case 1, we can show that the only color we can assign to these vertices is color 2. Furthermore, let X star be the set of vertices which have a neighbor in X, but which are non-adjacent to all the vertices in W. We can see that we can assign color 1 or color 3 to the vertices in X star. There might be some vertices left, and the remaining vertices all have a neighbor in Y. We now can show that all vertices in Y star, the remaining vertices, cannot receive color 1. For a contradiction, suppose that one vertex receives color 1. As there are no bichromatic 4 paths, and as each vertex has a neighbor in Y, we know that this vertex cannot receive color 3. And for some similar reason, it cannot receive color 2. So that means there is no option left for coloring this neighbor in Y. For that reason, all vertices in Y star have to receive color 2 or color 3. Okay, so let's go to the vertices that have distance 3 to V0. First of all, let T1 be the set of vertices which have at least 2 neighbors in W star. As there is no bichromatic 4 path, we find that the only color we can assign to the vertices of T1 is color 1. Next, let T2 be the set of vertices which have exactly 1 neighbor in W star. So we see that we can only assign color 1 or color 3 to these vertices. Now we find that all other vertices have no neighbor in W star. And we let S1 be the set of vertices which have no neighbor in W star, but a neighbor in T1. And so we see that we can assign color 2 or color 3 to these vertices. Furthermore, let S2 be the set of vertices which have no neighbor in W star, but at least 2 neighbors in T2. So we can assign color 1 and color 3 to such a vertex, but not color 2. For a contradiction, suppose we assign color 2 to such a vertex. As there are no bichromatic 4 paths, we find that the 2 neighbors in T2 have to receive different colors. so at least one of them has to receive color 3. But now we find a bichromatic 4-path, and so such a vertex in S2 cannot receive color 2. At this point, it's a natural question to ask if there are some further vertices which are of distance 3 to B0. And indeed, there are such vertices. Well, we now use the fact that there is no 5 cycle in our graph. In particular, we need that there is no edge from a vertex in W star to a vertex in X star. And by this fact, we can show that each vertex, which is in none of the sets S1, S2, T1 and T2, is adjacent to a vertex in X star, which has a neighbor in X, that now has a neighbor in W. And as there are some further vertices, which also might be in one of the 4 old sets, we let R denote the set of all vertices which have the latter property. So now we can show that we cannot assign color 2 to the vertices in R. For a contradiction, assume that we assign color 2 to such a vertex. But then one of the 2 4-paths is bichromatic. And so that's a contradiction. Okay, we now have a list 2 assignment of our graph G. But for some technical reasons, this 2 list assignment cannot be extended to a 2 list assignment of our supergraph. And so in order to avoid these technical problems, we distinguish 2 further cases. Well, case 2a is that where we assume all the vertices in Y receive color 3. Somehow similar as in case 1 or as for W star, we find that all vertices in Y star have to receive color 2. And now that's a technical proof, but we can show that this 2 list assignment of our graph G can be extended to a 2 list assignment of our supergraph. And so let's go to case 2b, and here we assume that at least one vertex in Y receives color 2. As there is no bichromatic 4-path, we find that all vertices in X star have to receive color 3, and for some similar reasonings, we find that all vertices in R and all vertices in S2 also have to receive color 3. We now again have a list 2 assignment of our graph G, and in a technical proof we now can show that this list 2 assignment can be extended to a list 2 assignment of our supergraph, and that's the way how we construct our list 2 assignments of the supergraph. Let me restate our main theorem for star K coloring, and we find that there are some open cases, and these are particularly that where we have 3 colors and where we have as input graphs of diameter at most 4, 5, 6 or 7. Okay, so let's continue with our last coloring problem, and that's injective coloring. A vertex coloring in general is called injective if the union of every 2 color classes induces a graph that has no P3. In other words, we forbid bichromatic paths on 3 vertices in such a coloring. As a particular corollary, we find that all the vertices which are adjacent to a common vertex have to be colored differently. Such injective colorings are also known as L11 labelings. And in general, such L1 and 2 up to NP labeling for some integers n1 and 2 up to np are simply mappings from the vertex set of G to the natural numbers, such that when we have 2 vertices, let's say u and v, and there's a uv path of length I, then the distance between the 2 colors we assign to the 2 vertices u and v has to be at least ni. And so we can easily define a decision problem that takes as input a graph G and an integer k, and simply ask if the input graph G has such a labeling on at most k labels. So what's known for such labeling problems? Well, first of all, let me mention that the L11 labeling problem is well studied for graphs of bounded diameter, and the L21 labeling problem remains NP-complete on graphs of diameter at most 2. Here we prove that also the L11 labeling problems NP-complete for graphs of diameter at most 2. So that's all I want to say. Thanks a lot for your attention.